Namaskar. So, in today's session we will discuss about convolution integral. So, we will see how we can utilize convolution integral in our circuit analysis. So, let us start first understand what is the convolution integral. The term convolution means folding. So, folding means when you take the mirror image of a particular function, means you are folding across the y axis. So, the term convolution integral has come from that particular concept, and what does it mean we will see when we will discuss the convolution integral in detail. And this particular integral is very important tool for the engineers, because it provides a means of viewing and characterizing the physical systems. For example, if you have the impulse response of a particular system, that is ST, which we discussed in our previous lectures. So, if you know the impulse response, you can find the response yt for any system with the excitation of xt. So, this is very important and very strong integral to find out the response of a system, the impulse response of which is known. So, how we will achieve the convolution integral? The convolution integral is defined like this, where the system response is yt and we integrate between minus infinity to infinity x lambda into h t minus lambda d lambda. So, h is your this impulse response, and x lambda is means lambda is anyway the dummy variable. So, x lambda is the excitation x t. So, when you take the convolution of both, that is x and t, then you will get the response y t. So, this integral is called as a convolution integral. How we will represent? We represent it in the asterisk form. So, what we say that y t is equal to x t, this is not a multiplication, this is asterisk and h t. So, we can say that basically the y t is convolution of x and h functions, and the lambda which we discussed in the previous slide was dummy variable, and this would be the convolution. Basically, the asterisk will represent the convolution of two functions. Now, the above equation states that the output is equal to input convolved with the unit impulse response, because unit impulse response we know, and we know that the new function is x t. So, we can find out the response of the system when we know the unit impulse response. Now, the convolution process is commutative, that means if you interchange the position of x and h, the output is not going to change. That means convolution of x and h will be same as convolution of h and x. So, in the integral form, what you will represent? Y t would be written as minus infinity to infinity integral x lambda h t minus lambda d lambda, or you can also represent integral minus infinity to infinity h lambda x t minus lambda d lambda, because both are commutative. That means that the order in which two functions are convolved is immaterial. Now, the term convolution, how you will define the two signals which consist of time reversing of one of the signal, shifting it and multiplying it point by point with the second signal, then and integrating the product, then the output would be the convolution of two signals. So, how we will visualize? let us take one example so that you can understand the concept. Let us say that there are two functions. One is, let us say it is a function like this, and second is a function like this. Now, when we say the convolution of two signals means time reversing of one of the signal, means you are folding that signal. So, when you suppose if you fold that signal, what you will do, you will take the mirror image of that signal. So, this will become like this. Shifting it means you can shift it at some location, because it will be varying with respect to time, and we will keep on shifting this signal across the axis, and we will try to find out the multiplication of this signal and this signal point by point, and then integrate it so that you can get the product. How we will do? So, let us say that you are putting a signal here, this particular signal is moving. So, it is moving from this side to, let us say this is a axis lambda. So, you are shifting this, may be like if you say this is h t minus lambda. So, you will shift this particular function. So, what you have defined, the integral h lambda into x t minus lambda. So, what you have to do now, you have to take the product of two and then sum up, because integration is nothing but the summing up the product of these two signal over a particular time period. So, when you shift, if let us take the axis and see how it is getting mixed. So, at one particular time the signal would be like this. So, you will have total product and the sum of those product, which is the area like this, and then after some time this will become like this, right, and after some time it may leave and will become like this. So, what is happening now, that the signal is shifting, because you are shifting it. So, signal is shifting, we will only shift one, second one is stationary. So, we are shifting with respect to the value lambda. So, at this axis it is shifting, and we are trying to find out the value of the product at each and every point, and then you are integrating, means you are summing up all the products, and then you are again taking another location and finding out the product. So, finally, if you see and if you trace the product and the integration of these two functions, so it may look like this. So, this would be considered as a convolution of these two signals. So, this is the basically the output which you will get when you apply convolution integral between two functions. So, we will discuss more in detail when we will proceed in this particular lecture, and we will try to understand with the help of few more examples, so that you are clear about the meaning of convolution integral. Now, the convolution integral is the general one, it applies to any linear system, but the convolution integral can be simplified if we assume that the system has two properties. So, what are those two properties? First is that x t is equal to 0 for t less than 0. It means that your integration, which is now from minus infinity to infinity, will reduce to integration between 0 to infinity for the convolution integral. And second property what we can use is that system's impulse response is causal. That means h t is equal to 0 for any time t less than 0. So, if this property holds, you can say that ht minus lambda, that is this function, would be 0 for t minus lambda less than 0, or you can say that for lambda greater than t, the above equation will now become the convolution of h and x will be nothing but integration 0 to t x lambda h t minus lambda d lambda, because for any value lambda greater than t, this will become 0. So, when we say that the functions are following these two properties, first function is 0 for t less than 0 and second is causal, means it is 0 for lambda greater than t, then we get the reduced integral. So, integral will now be between 0 to t x lambda h t minus lambda d lambda. Now, let us see few of the properties of convolution integral. We are not going to derive it because it is not in our like scope of the current subject, but we have to keep in mind that there are few properties which we will use when we will progress in this particular course. So, first property is convolution of h and x is commutative, means you can exchange the locations of h and x and the convolution integral will hold. Second is distributive property, means if you have the function like x plus y and you want to take the convolution with f, then it is distributive, means you can take convolution of f and x and f and y separately and then you can sum them up. Now, third is associative property. So, you can either take convolution of x and y first and then the product is convolved with f, or you can take the convolution of f and x first and then the product will have the convolution with y. So, since it is associative, you can use either of the method for getting the convolution integral. Now, next is the property when the function is convolved with the unit impulse function, then you can, when you integrate between minus infinity to infinity f lambda delta t minus lambda d lambda, this will be 1 only when t is equal to lambda. So, finally, the output which you will get is nothing but f t. Similarly, if you are convolving with the delta t minus t naught, that is time shift impulse function, so you will get the output as f t minus t naught. If you are taking the convolution of f t with the derivative of unit impulse, you will get the output as derivative of function f t. Now, if you are taking convolution of f with the unit step, the output would be minus infinity to t f lambda t lambda, because for lambda greater than t, the unit step would be 0. So, that is why the value of lambda up to t is the upper integral component for the convolution of f with unit step function. So, these would be the major properties which we will keep on using when we will use the convolution integral in various circuit concepts. Now, before learning how we can evaluate the convolution integral, let us first understand how the convolution integral is linked with the Laplace transform. So, suppose if you have two functions like f1 and f2, the Laplace transform of those time varying functions are f1s and f2s. Then if you take the convolution of f1 and f2, then you will say that the output of the convolution of f1 and f2 and when you take the Laplace of the convolution of f1 f2, you will simply say that the Laplace of the convolution of f1 and f2 would be nothing but f1 f1s multiplied by f2s. So, it means the Laplace transform of the convolution of f1 and f2 is simple multiplication of f1s and f2s. Now, let us see how we can justify this particular concept, whether it is true or not. So, let us see that there is a function f t which is a convolution of f1 and f2. So, you will define it like integral 0 to t f1 lambda f2 t minus lambda d lambda. Now, if you take the Laplace of function f1, so f1s you can simply write as 0 to infinity f1 lambda e to the power minus s lambda d lambda. Now, if you multiply this f1s Laplace, that is what we have just now computed. So, if you multiply with f2s, you can simply write the function as 0 to infinity f1 lambda into f2s, that is the multiplication done on both sides, multiplied by e to the power minus s lambda d lambda. Now, if you use the time shift property, because if you see this holds the, you can say that when you use the time shift property, this can be converted into the Laplace of the function f to t minus lambda u t minus lambda, being the e to the power minus s lambda as time shift component. So, what you can now write, the term in bracket which is f2s e to the power minus s lambda is nothing but the Laplace of f2 t minus lambda u t minus lambda, or in the integration form you can write 0 to infinity f2 t minus lambda u t minus lambda into e to the power minus s lambda dt. Now, if you put this value in the above equation, what you can write, f1s into f2s is nothing but integration of 0 to infinity f1 lambda into, now in f2s e to the power minus s lambda you will substitute the value which you just computed, that is nothing but the Laplace transform of time shift function f2. So, if you put the value here, you can simply say that it is 0 to infinity f2 t minus lambda u t minus lambda e to the power minus s lambda dt. Now, if you see, this will hold until t is greater than lambda. When the lambda is greater than t, this particular function will become 0. So, what you can write in terms of integral, first we will interchange the order of integration. So, now it will become 0 to infinity, and in the second integral we will say that it is ranging between 0 to t because of the unit step time shift function, and you will say that it is f1 lambda into f2 t minus lambda dt, and e to the power minus s lambda d lambda will take out for the second integral. So, you can rearrange this particular expression in this particular form. Now, if you see this particular term, this is nothing but the convolution of f1 and f2. So, what you can write, the integral is therefore the convolution of f1 and f2. So, if you see this, you will simply represent it as f1 maybe t convolution of f2 t, and then the outer integral is nothing but the Laplace of the convolution of f1 and f2. So, you can simply write f1s into f2s is nothing but Laplace of the convolution of f1 and f2. So, you can simply say that the convolution in time domain is equivalent to the multiplication in S domain. So, this is how you get when you rearrange the terms and justify that the convolution is of convolution of f1 and f2 is multiplication in S domain. Now, let us take one example so that you can understand how we will utilize this particular concept. Let us see that x t is nothing but 4 into e to the power minus t, h t is 5 into e to the power minus 2 t, and when we apply the above property, the convolution of h and x is nothing but inverse Laplace transform of h s into x s. What is h s? H s can become 5 upon s plus 2 because it is a Laplace transform of h t. Similarly, x s is nothing but Laplace transform of x t. So, you can simply write it as 4 upon s plus 1. Now, if you rearrange the term within the square bracket will become 20 upon s plus 1 plus minus 20 upon s plus 2. So, if you take now the inverse Laplace transform of the term which is there in the square bracket, it will become 20 into e to the power minus t minus e to the power minus 2 t. So, what you can say now, the convolution of 4 e to the power minus t and 5 into e to the power minus 2 t is nothing but 20 into e to the power minus t minus e to the power minus 2 t, and this would be time t greater or equal than 0. So, with this you can simply see that when you apply the Laplace transform of the convolution, you can easily get the answers. Now, there is another point which we have to remember with respect to this property which we have just now calculated, because although this convolution of two signal which we saw in the previous case is it looks simple, but sometimes finding the inverse may be tough. Why? Because the moment when you have f1s and f2s, the product of both is complicated, then it would be difficult to utilize the concept of convolution using Laplace transform. Then what you will do? You will use some alternate technique. Another case is that when f1 t and f2 t are available in the form of some experimental data and there is no explicit Laplace transform of these two functions available. So, when this particular condition happens, you will not be able to get the Laplace transform of f1 t and f2 t, and then getting the convolution of f1 and f2 using the Laplace transform product would be difficult. So, what you have to do? You have to use the alternate approach, that is called the graphical approach, to find the convolution of two signal in time domain. What is the graphical procedure? Graphical procedure says that the 4 steps which we are describing below will be followed to find out the convolution integral of two functions. First is folding. Folding means you will take the mirror image of h lambda about the ordinate axis and obtain the value of h minus lambda. Now, you have to displace the function. So, that means shift or delay h minus lambda by t to obtain h t minus lambda. Now, next task is that you have to multiply, find the product of h t minus lambda and x lambda, and then integrate for a given time t and calculate the area under the product h t minus lambda x lambda for time lambda varying between 0 to t, and then you will get finally the value of y t. Now, the folding operation in step 1 is the reason of the term convolution. So, this is what we discussed in the first slide, that folding, that is nothing but taking the mirror image, is the reason of calling this particular integral as convolution integral. Now, the functions h t minus lambda scans or slides over h lambda. So, this is what we saw in the example which we were discussing, that when you slide over the particular given signal and you take the product of each and every term and then you sum it up, so that you get the value of integral. So, it means that you will utilize the shifting function which will scan or slide over the x lambda to get the final integral. So, in view of this, the superposition procedure, because this is also a superposition of function h t minus lambda over x lambda, the convolution integral is also known as the superposition integral. So, you can now see that the convolution integral can also be called as a superposition integral, because it contains the superposition procedure also. So, to apply the 4 steps, it is necessary to be able to sketch x lambda and h t minus lambda. So, for the graphical approach, we have to keep in mind that we can sketch both of the functions, and means we can plot both of the function on x y axis and then get the x lambda from the original function x t. This involves merely replacing t with a dummy variable lambda, then sketching h t minus lambda is the key to the convolution process, because it involves reflecting h lambda about the vertical axis and shifting it by t. So, analytically we obtain h t minus lambda by replacing every t in the h t by t minus lambda. Now, since the convolution is commutative, it is sometimes more convenient to apply step 1 and 2 to x t instead of h t. So, we have to look at the functions x and h, and we can with the help of just understanding the sketch of x and h, we can easily find out which one we have to fold and slide over the other one. So, like in the previous case, what we did, that we folded this particular function. If we fold this, we will not be able to differentiate between original and the folded function, and we will not be able to explain it. So, that is why I folded this function. Similarly, when you actually calculate the convolution using graphical approach, you can see which one is the best for the folding. So, this you have to always keep in mind when you are using the graphical approach. So, now we will take one example. So, what we can do, we can stop our discussion today at this point, and we will continue our discussion on convolution integral in the next lecture also. Thank you.